In this workshop, we're going to look at how molecular orbital energy level diagram and electron configuration determines the stability of molecules and the ions which are derived from the molecules. And in this particular case, we're going to look at three diatomic molecules, H2, He2, and Li2, and ask which of these diatomic molecules, if any, will become more stable upon the loss of an electron. Now in this case, the electron is going to be gone from or taken from the highest available molecular orbital. And that electron, when it leaves, will change the bond order of the molecule, which has now become an ion, depending on whether the highest occupied molecular orbital is a bonding molecular orbital or an antibonding molecular orbital. So we need to look at these three molecules' energy level diagrams to see what happens to the bond order when we remove an electron. In the first case, H2, we can see that the two valence electrons for the molecule occupy the sigma bonding molecular orbital right here. And the sigma antibonding molecular orbital, both of these derived from 1s atomic orbitals, that sigma antibonding one is empty. Therefore, the bond order is equal to 1/2 of the number of electrons in bonding molecular orbitals will be 2 minus the number in antibonding molecular orbitals. That'll be 0. And so we would expect that value to be 1. Okay? So we look at H2. The bond order is, as we said, 1. If we look at He2, there are 2 electrons in the sigma bonding molecular orbital, and there are 2 electrons in the sigma antibonding molecular orbital. So the bond order will be 1/2 of 2 minus 2, or 1/2 of 0, and that'll just be 0. So He2 has a 0 bond order. If we look at Li2, Li2 has molecular orbitals based on the 2s atomic orbitals. There's a sigma 2s and a sigma star 2s. And there are 2 valence electrons, one from each lithium. So those 2 electrons will be in the lowest molecular orbital, which would be the sigma bonding molecular orbital. The bond order, of course, would be 1/2 of 2 minus 0, and that'll be 1. So the bond orders of the molecules are 1, 0, and 1. Now we want to look at what happens when we form the ions. H2 will form H2 plus by losing one of the electrons in the sigma bonding molecular orbital. So if we want the bond order of the ions, we take the electron away and recalculate the bond order. So if we look at this, now we have 1 electron in the sigma bonding molecular orbital and none in the sigma antibonding molecular orbital. So the bond order will be 1/2 of 1 minus 0, and that'll be 1/2. So H2 plus has a bond order of 1/2. If we look at He2, the highest occupied molecular orbital is the sigma star 1s up here. It has 2 electrons. And so for it to lose 1 electron, we would expect one of these electrons to be the one that's lost. And for He2 plus, then there'll be 2 electrons in the bonding molecular orbital and only 1 in the antibonding molecular orbital. Now what does this mean with respect to the bond order? It clearly means that the bond order is going to be 1/2 of 2 minus 1, or 1/2 of 1, it should be 1/2. So by taking an electron away, the bond order went from 0 up to 1/2. Well, what happens with lithium? There are 2 electrons in the sigma 2s and none in the sigma 2s star. So if we form lithium 2 plus, then there will only be one electron down here. The bond order will be 1/2 of 1 minus 0, or 1/2. Now, as we look at these, hydrogen went from 1 down to 1/2 when we took away one electron. Dilithium went from 1 down to 1/2 when we took away one electron. But dihelium went from 0 up to 1/2. So that means the only molecule here nominally that will increase its stability upon losing an electron would be He2. And so the answer to the workshop is number 2, He2.